In this e-content, we are going to see the methods to solve the first order partial differential equations. So there are four types to solve the first order partial differential equation. Type 1, it does not contain x, y and z explicitly. Type 2 is Clairaut's form, and in type 3 there are three cases. In the first one, x occurs explicitly. In the second and the third one, y and z occur explicitly. So in type 4 we are going to see about separable equations. So type 1 is of the form f of p comma q is equal to 0. X, y, z do not occur explicitly. So we can find out four types of solution: complete solution, complete integral, singular integral and the general integral. So we'll assume z equal to ax plus by plus c is a solution of f of p comma q is equal to 0. We know p is equal to dou z by dou x equal to a and q is equal to dou z by dou y is equal to b. So we'll substitute the value for p and q as a and b in the first equation. So we'll get the complete solution as z is equal to ax plus by plus c where f of a comma b is equal to 0. So to find the complete integral, we'll solve for b from a of b comma b equal to 0. So we get b is equal to phi of a. Then z equal to ax plus phi of a into y plus c is the complete integral. To find the singular integral, we consider z equal to ax plus phi of a into y plus c. We've got to differentiate this equation partially with respect to a and c completely. So on differentiating with respect to c, we can observe that 0 is equal to 1. So this is an observed result. So no singular integral exists. In order to find the general integral, we'll put c is equal to f of a and z equal to ax plus phi of a into y plus c. So we'll get an equation which is in terms of a. So on differentiating this equation, we'll get 0 is equal to x plus y into phi dash of a plus f dash of a. So eliminating a from 5 and 4, we will get the general solution. So type 1 is illustrated by means of a problem. We've got to solve root p plus root q is equal to 1. So we'll assume z equal to ax plus by plus c is the solution. We've got to put p equal to a and q is equal to b in 1. So we'll get root a plus root b is equal to 1. So z equal to ax plus by plus c is the complete solution provided root a plus root b is equal to 1. To find the complete integral, we should find b from root a plus root b equal to 1. So b is equal to 1 minus root a the whole square. So z equal to ax plus 1 minus root a the whole square into y plus c is the complete integral. So to find the general integral, we should put c is equal to f of a in z equal to ax plus 1 minus root a the whole square. So we will get the resulting equation as z equal to ax plus 1 minus root a the whole square into y plus f of a. So differentiating with respect to a, we get 0 equal to x minus 1 by root a into 1 minus root a into y plus f dash of a. Eliminating a from the third and the fourth equation, we'll get the general solution. So we've got to differentiate equation 2 with respect to a and c in order to get the singular integral. But when we differentiate with respect to c, we get 0 is equal to 1, which is an observed result. So the singular integral does not exist. Method 2 is Clairaut's form. So the general form of Clairaut's equation is z equal to px plus qy plus f of p comma q. We know that p is equal to a and q is equal to p. So if we substitute p is a and q is b in the given equation, we'll get z equal to ax plus by plus f of a comma b, which is the complete solution. In order to find the singular integral, we've got to differentiate the second equation with respect to a and b partially. So we'll get x plus dou f by dou a equal to 0 and y plus dou f by dou b is equal to 0. By eliminating a and b from the third and the fourth equation, we'll get the singular integral. In order to find the general integral, we should put b is equal to phi of a in the second equation. So we'll get an equation only in terms of a, and we should differentiate it with respect to a partially. So we'll get 0 is equal to x plus phi dash of a into y plus x star. So on eliminating a from 5 and 6, we will get the general integral. So we demonstrate Claridge's equation with a problem. So the given problem is z equal to px plus qy plus p squared minus q squared, which is a function of p and q. So to find the complete solution, we should put p equal to a and q equal to p in the given equation. So the complete solution is z equal to ax plus by plus a squared minus b squared. To find the singular integral, we must differentiate z equal to ax plus by plus a squared minus b squared partially with respect to a and b. We get a is equal to x minus x by 2 and b as y by 2. So we should substitute this equation in z equal to ax plus by plus a squared minus b squared. So the resulting solution is 4z equal to y squared minus x squared, which is the singular integral. To find the general integral, we should put b is equal to phi of a in z equal to ax plus by plus a squared minus b squared. So we get z equal to ax plus phi of a into y plus a squared minus phi of a the whole square. We must differentiate this equation with respect to a and eliminate a from 2 and 3. We will get the general integral. In type 3, we have got 3 major parts. In the first one, x will occur explicitly, in the second one y will occur explicitly, and in the third one z will occur explicitly. So in the first one, x will occur explicitly, and we know that dz is equal to p dx plus q dy. So we will assume q equal to a. So the given equation becomes f of x comma p comma a is equal to 0. So we are determining p in terms of x comma a. So p is equal to phi of x comma a. So dz becomes phi of x comma a into dx plus a into dy. So on integrating, we get z is equal to f of x comma a plus ay plus c, which is the complete integral. Similarly, we have to find the solution for y f of y comma p comma q. So here we are going to assume p is equal to a. So the given problem becomes f of y comma a comma q is equal to 0. So we find q in terms of y comma a, and the resulting equation will be dz is equal to a dx plus phi of y comma a into dy. So z is equal to ax plus phi of y comma a into dy plus c. So the final solution will be z equal to ax plus f of y comma a plus c, which is the complete integral. So this is illustrated by means of an example. So we've got to solve p is equal to 2qx. Since x occurs explicitly, we'll put q is equal to a. So p is equal to 2ax. So in dz is equal to pdx plus qdy, we'll substitute the values of p and q. So we'll get dz is equal to 2ax plus a dy. So on integrating, we'll get z equal to ax squared plus ay plus c, which is the complete integral. So if we differentiate this equation with respect to c, we get 0 is equal to 1, which is an absurd result. So singular integral does not exist. We will put c is equal to f of a in equation 1. We get z equal to ax squared plus ay plus f of a. If we differentiate it with respect to a, we will get 0 equal to x squared plus y plus f dash of a. So if we eliminate a from the second and the third equation, we get the general integral. So to illustrate problems which contains y explicitly, so we'll solve pq is equal to y. So y occurs explicitly. So we'll put p is equal to a. So the value of q is equal to y by a, and we'll substitute the value p is equal to a and q is equal to y by a, and dz equal to p dx plus q dy. So we'll get dz is equal to a dx plus y by a into dy. Integrating, we get z equal to a plus y squared by 2a plus c. This is the complete integral. If we differentiate with respect to c, we get 0 is equal to 1. So singular integral does not exist. If we put c is equal to f of a, we get z equal to a plus y squared by 2a plus f of a. If we differentiate this equation with respect to a, we get 0 equal to a plus y squared by 2a plus f dash of a. If we eliminate a from the second and the third equation, we will get the general integral. type 4 problems. So this will be of the form f of x comma p is equal to phi of y comma q. So over here I am going to put each of these expressions as f of x comma p is equal to phi of y comma q is equal to a. If I solve for p in the first equation, I will get p is equal to f1 of x comma a and q is equal to phi 1 of y comma a. We know that dz equal to p dx plus q dy. So dz is equal to f1 of x comma a into dx plus phi 1 of y comma a into dy. So integral dz is equal to integral f1 of x comma a into dx plus phi 1 of y comma a into dy plus d. So this equation gives us the complete integral. So we'll demonstrate this by means of an example. So we have got to solve p minus x squared is equal to q plus y squared. So over here we can find out that we've got p and x on one side and we've got q and y on the other side. So we'll put p minus x squared is equal to a and q plus y squared equal to b. So from the first one, p is equal to x squared plus a and q is equal to a minus y squared. So we know dz equal to p dx plus q dy. So dz is equal to x squared plus a into dx plus a minus y squared into dy. So integrating we get z equal to ax plus x cubed by 3 plus ay minus y cubed by 3 plus b, which is the complete integral. So if we differentiate 1 with respect to b, we get 0 is equal to 1, which is the singular integral, and the singular integral does not exist. So if we put b is equal to f of a, we get z equal to ax plus x cubed by 3 plus ay minus y cubed by 3 plus f of a. If we differentiate this equation with respect to a, we get 0 is equal to x plus y plus f dash of a. So if we eliminate a between second equation and the third equation, we will get the general solution. So these are the 4 types of equations which are solved in first order partial differential equations. Thank you.